So good morning, everybody. Our senior project focused on a wind-powered irrigation system. My name is Mike Lang.
I'm Justin Haag.
Jesse Putnam.
Curtis Mulhaul, Jonathan Deutsch,
And Tim Kinnard.
Our faculty advisor for this project was Dr. Hryniewicz. So to begin our presentation, we'd like to start with the background of our project. So the Foundation is an organization located in Haiti. They work to improve the well-being of families located in farming areas within Haiti. They reached out to Widener University School of Engineering for help with their situation, as they identified a need for irrigation systems in remote areas of Haiti, where electricity is not easily accessible. They also located a specific man-made well, which can be seen in the picture to your right, where the water level is 10 feet below ground level and located next to several retention ponds. The Foundation is highly considering implementing a wind-driven pumping system to move the water from the well to these retention ponds, so it's more easily utilized by these Haiti farmers. The main goal of our project is to perform a feasibility study of a wind-powered irrigation system with the scope of designing, manufacturing, and testing a scaled-down prototype. In doing so, there are certain design criteria involved with the full-scale design. Our target flow rate is at least 3 gallons per minute, which is recommended to us by the Foundation. Also, a cut-in speed of less than 4.5 miles per hour. And cut-in speed just refers to the speed necessary to start spinning the blades. There are also several design constraints involved. The main constraint being the very low wind speeds in the area of only 7 to 9 miles per hour. Another constraint includes a blade diameter not exceeding 15 feet. And we also would like to keep our costs low and make it easy to manufacture so it's more affordable and easier to implement for the people in Haiti. So our approach in the beginning of the year was to divide this project into 4 main components that are interconnected, meaning that if a modification is made to one of these components, it will therefore affect the other components as well. 4 components we will discuss next include the turbine blades, a pumping system, transmission system, and the foundation and structure. Next, I'll hand it over to Justin to explain the blade portion of our project.
Thank you, Mike. So before selecting a wind turbine, it's important to know how much power is actually being produced from wind. See in the top left corner here, that wind power equals 1/2 times the density of the wind times the wind speed, area that the wind is occupying, or in this case, the area of our turbine. Notice that wind speed is cubed, so it has a dominating effect in the equation. Because of this, it's important that we select a wind turbine that is as efficient as possible in harvesting available wind power and mechanical power. This metric is known as power coefficient, or CP for short. 3 wind turbine models you see here are the most common ones on the market today, with the American windmill often being used for irrigation purposes, but it has relatively low power coefficients due to drag-based design. The airfoil turbine, on the other hand, is a lift-based horizontal axis design that has relatively high power coefficient, higher than the other ones that you see. For this reason, we chose to go with the airfoil turbine. For scaling down our model, we chose to go with a 3-to-1 scaling, and this meant that we'd be making a 5-foot diameter turbine. Dynamically, for our results to be meaningful, there are 2 non-dimensional parameters that need to remain in our full scale and our scaled down model. First is Reynolds number, which characterizes the flow of the moving fluid. Second is tip speed ratio, which compares blade tip speed to the wind speed, actually propelling the turbine. Keeping these quantities consistent, we're able to find what our required wind speed is for our prototype, as well as how fast our prototype is spinning. We found that our prototype would need 3 times the full-scale wind speed. We found that our prototype would be operating 9 times faster than our full-scale. For our blades, we designed and optimized our blades using iterative MATLAB code based on the blade element momentum theory. This method, we split our blades up into 20 equal length segments, where we calculated the force on each segment using relative wind speeds and the lift and drag coefficients what we were observing. After integrating over the blade radius, we could then find things such as power coefficient, total power, and other important variables. This graph in the bottom right shows our twist angles for each blade segment go along the blade that was calculated in order to ensure an optimal angle of attack of 6 degrees. It's also helpful in manufacturing the curvature of our blades. Overall, we were able to optimize our design for our low wind speeds by selecting a NACA 0012 airfoil that has the listed parameters here. So for manufacturing, we actually 3D printed our blades in spans using PLA plastic. When making the solid model, we had a rectangular hollow cross-section that went all the way through the blades, and coupled this with two holes that went through the base of each span. What this did was it allowed us to actually slide each span onto a bar stock, where we were then able to fasten and tighten everything together by pressing roll pins through the holes and through the bar stock. The picture you see in the right here shows how we actually balanced our blades. We actually made a homemade balancing stand where we were able to get a full perfect static balance by adding weight only to the hub, which is better for a dynamic balance as well. Now I'll hand it off to Jesse, and he'll tell you a little about the pumping system.
Thank you, Justin. So in considering design for the pumping system, there were constraints that we needed to follow. First that we were looking for was an ease of integration between the pump and the turbine itself. We wanted something simple that runs at low shaft speeds and requires little maintenance. We needed to be able to operate with low amounts of applied startup torque, and most importantly, be cost efficient. First pump we considered is the common centrifugal pump. Although simple in design, these pumps pass dirt particles poorly and require half shaft or high shaft speeds to run efficiently. For these reasons, we investigated other options. Looking at the Archimedes screw pump, these pumps offer good flow and operate well at low shaft speeds, but due to its angle and size, integrating it into our system would prove difficult, and implementing it into the well in Haiti would be even harder. Next, we looked at the progressive cavity pump. These are great pumps that use complex geometry to move fluid through moving chambers within the pump. They operate well at low shaft speeds and are able to overcome large amounts of head pressure, yet they are extremely expensive with prices that can exceed $20,000. So finally, we looked at the single acting piston pump at the bottom right. These are common for windmill applications because they can convert the rotational motion of a crankshaft into the translational motion of a piston. On the upstroke of the piston, fluid is sucked into the chamber, and on the downstroke, it is discharged. Not only are these pumps simple, but they are cost efficient. We decided to go with the piston pump by making a modification to it. Instead of a single acting piston pump, we wanted to use a double acting piston pump. Same concept, except that it includes 4 check valves, a suction chamber, and a discharge chamber. The advantages to this are it discharges fluid on both the upstroke and the downstroke of the piston. It makes the system more efficient, and it lowers the required starting torque by almost half. The way we built this was buying a simple hand bilge from Home Depot, 1.5 inch PVC and several fittings along with 4 check valves, and we assembled and glued all the parts together to get the pump that you see on the right. And once we had our pump finished, we needed a way to integrate that to our turbine through a transmission system, which Curtis is now going to tell you about.
Thank you, Jesse. On the left-hand side here, you can see our SolidWorks design. We use SolidWorks to not only design, but also analyze our system before we built the prototype, which is shown on your right. It's important to notice that the input of the turbine blades of the rotational motion drives a pulley system and slows down the RPMs of the output reciprocating motion on our pump. There are a few key components of our transmission system, one being our wooden frame that was made out of 2x4 wood. Also, we had a 4L V-belt pulley system with an 8.2 to 1 speed reduction. Here, if the blades were spinning at 600 RPMs, the output on the pump would be around 73 RPMs. If you look at the lower left picture, here's our variable crank. That was actually used to test different crank lengths in the lab from 3/4 of an inch to 9 inches. Also, in the lower center is our pump connector. This pump connector connected the connecting rod to the piston rod. This was actually designed in SolidWorks and 3D printed out of ABS plastic. The bottom right, we have one of our bearings. For our total in our system, we had 4 bearings. These were low friction, permanently mounted bearings. They were also self-aligning, which allowed to reduce the vibration in the system. Also, we did run into an issue when we were testing. Our piston rod actually buckled. This is because the piston rod was made out of wood. In order to overcome this, our team got together. We machined and fabricated an aluminum rod to replace the wooden rod that actually buckled. So now that we're done with our design and our build, we're going to move into testing. So there's 2 types of testing. First, I'll talk about the testing of the performance of the turbine blades alone. And then later on, Jesse will talk about testing of the whole system. So if you look at the picture on the right, you can see that we use the exit of our wind turbine, or our wind tunnel, for our wind source on the project. On the right-hand side is our torque sensor. Directly connected to that is the shaft of our turbine. On the right-hand side, on the lower picture, we used a ratchet strap to act as a brake on our torque sensor that acted as a pre-applied load to our turbine. So to test the startup torque, we applied a full brake with a ratchet strap to the torque sensor, and we measured the torque at those varying wind speeds. After that, we tested the operating power by varying the brake torque with the ratchet strap. And here we also tested the torque and the RPMs at those different speeds. These methods were used to validate our analytical design. Now I'm going to pass it on to John to talk more about the ununiform wind coming out of the exit of our wind tunnel.
Thank you, Curtis. So the main testing challenge we faced was non-uniform wind over our blade area. And so this was not ideal for testing, and it did pose the challenge of what wind speed to use when analyzing our results. What we did was we created a velocity profile seen on the right. We divided this velocity profile into 40 small sections. And for each section, we calculated the wind power. By adding up the wind power for each section, we could get total wind power. And from that power, we could get an equivalent wind speed. We created a graph that allows us to determine the equivalent wind speed at any wind tunnel setting with a maximum observed testing speed of 14.2 miles per hour. So now I'm going to transition into some results, all of which are presented in terms of equivalent wind speeds. First, we have turbine startup torque. As you can see, as the wind speed increases, the startup torque also increases with a maximum observed startup torque of 18 pounds at our maximum testing speed. And then for turbine operating power, on the left is our analytical results from the iterative MATLAB code, and on the right is our in-lab experimental results. As you can see, we're able to achieve a power coefficient of about 0.3. Comparing that to the analytical results of about 0.38, we do fall within about 25%. And so to conclude, we can say that our experimental results validate that the lift-based airfoil design was the best option, as it doubled the maximum power of the American windmill and equaled the max power of the Savonius wind turbine. And so with better wind uniformity, we believe that we could get better power coefficients. I'm going to pass it over to Jesse to talk about testing with the pump.
Hey, John. So we tested our full prototype assembly looking for both flow rate and overall efficiency data. We tested it inside in the lab using the exhaust of the wind tunnel and outside on the roof of this very building. We tested 3 different crank lengths inside and 1 3-inch crank length outside. We plumbed the suction side of the pump into a bucket of known volume, and then the discharge side of the pump up through a 10-foot pipe to give us our desired head pressure. Then divided the volume of the bucket by the amount of time it took for the pump to move that water to calculate our flow rate and our overall efficiencies. So looking at the graph on the left, as our wind speed increased, our flow rate increased. Also, as we increased our crank length, our flow rate increased with that as well. Our largest flow rate was about 3.5 gallons per minute. That was using our 3-inch crank length at our outdoor testing. Not only was the wind speed the fastest outside, but because we weren't using the wind tunnel, it was also the most uniform. Looking at the graph on the right, as our wind speed increased, our overall efficiency decreased. But as our crank length increased, our overall efficiency increased with it. Now we noticed while we were testing, we were increasing the crank length, which is increasing the torque and the load on the system. Yet the turbine blades were remaining the same speed. This showed us that our pump was undersized for this system. The turbine was producing more power than the pump could handle, thus giving us the low efficiencies that you see below. Ways that we could rectify this would be increasing the crank length even farther, increasing the transmission ratio, or increasing the diameter of the pump that we use. Next, I'm going to hand it off to Tim, who's going to go over the structure.
Thank you, Jesse. So now that's been demonstrated, the foundation, it's possible that we can get their pumping requirements to the windmill. They have to decide if it's feasible for them to emplace a structure in Haiti. We looked at several different tower designs and ultimately decided with a lattice tower to fit the sizes of the double action piston pump, and as well to minimize cost, we're going to go with a private company to build it. Aeromotor windmills, that'll cost about $5,300. That doesn't include the cost of shipping. Also, Haiti's or the Foundation's planning to use retention ponds to distribute the water. However, that's downhill from their proposed irrigation location. So we're recommending that they build storage tanks in an elevated position so that they can disperse the water more easily. Due to the USDA requirements, we weren't able to take any soil samples, and for budget requirements, we couldn't go to Haiti for that. So for future testing, we're looking into possibly an outside firm that operates in the southern end of Florida and the Caribbean, so they can check for our soil samples to see if they can support the structure, as well as the foundation's requesting a 30-foot well. At this time, we don't recommend them going that deep since the water table is only about 10 feet down. But if they do want the 30-foot well, then more subsurface excavation is going to have to be done. Decide if they're going to hit any bedrock or depth of the well. I'm going to hand it off to Mike for a quick.
Thank you, Tim. So based on our results, we were able to draw several conclusions. We're able to achieve a maximum system flow rate of 3.47 gallons per minute while testing outside, and a flow rate of 3.16 gallons per minute while testing in the lab. Both of these do exceed our target flow rate of 3 gallons per minute. We're also able to obtain a theoretical power coefficient of up to 43%, despite our wind turbine having a low Reynolds number. We demonstrated a power coefficient of up to 30% while testing in the lab, despite non-uniform wind. We concluded that if a larger pump were to be incorporated into our design, that would therefore increase the overall system efficiency as well as increase the flow rate. Despite our pump testing being inconclusive, we were able to estimate that with a proper pump in the system, we would exceed a flow rate of 20 gallons per minute, utilizing a 15-foot turbine, receiving 9-mile-per-hour wind speeds. And finally, we were able to determine that it is feasible to implement a similar system in Haiti, despite low overall system efficiencies and less than adequate testing wind speeds. Before we conclude our presentation, we'd like to acknowledge these four. A special thank you to ASME Philadelphia section and Widener University School of Engineering for funding our project. We'd like to thank the IF Foundation for providing us with this project, and we'd especially like to thank Dr. Hryniewicz for all of his help and support throughout the year. Before we conclude, this is a quick video of in-lab flow rate testing. Thank you. That concludes our presentation. We'd like to thank you for your attention and open the floor for any questions.
All right, we have time for a couple questions. Yes.
So we did, the airflow that we collected did happen to be symmetrical, but it is very good to be optimized for low Reynolds numbers. So when we put everything into the code, we actually tested a bunch of different airfoils, ones with camper, like you said, but the NACA 012 airfoil ended up being the better out of every single one.
Question? Yep. Go ahead.
Considering Haitian weather conditions.
So that's variable. However, a big thing with the Haitian weather conditions, they rarely get severe hurricanes, even though they are in the Caribbean. The destruction that they get from the more low-level hurricanes is because they're a poor country, they can't afford oil, and they don't have coal, so they cut down all their trees because they don't. Because of deforestation, they typically get a lot of flooding and landslides on the mountains when rains come. And that destroys all the crops. So it wouldn't, the tower is able to support it, but if there was severe weather conditions, it might not have anything to pump to.
The question. Go ahead.
There's natural wind on the roof of this building. We did. We went up there. Yeah, we went up there with an anemometer, and we made sure the wind was coming in at a constant angle. And then while we were running the tests, we had a film on the anemometer the entire time to get the wind speed at every second over the entire test for each flow rate. And then after that, we were able to analyze the data and be able to come up with an equivalent wind speed.
One more question. Go ahead. All right. Great job, guys. Thank you.
Thanks.